Hello, we continue to study the Z-domain analysis module of discrete systems. Today, we start the sixth part, Z-domain analysis method for discrete systems. Section 6, Inverse Z-transform partial fraction expansion method. Let's take a look. The basic principle of partial fraction expansion method, according to the discrete time series, the form of the transformation is generally as follows. That is, the form of the rational fraction of z. Then we have to perform partial fraction expansion on this rational fraction. We can first review partially expanded form used in the Laplace inverse transformation. We know that in the Laplace inverse transformation, the most basic form of function we use is this representation of Laplace transformation corresponding to the unilateral exponential signal is in the form of 1 over s minus alpha. Then as for it, we can easily expand f of s, partial fraction, so as to find the inverse Laplace transform. Then let's compare. We are familiar with the form of the transformation. This is about Carroll sequence, anti-Carroll sequence. In the case of different convergence domains, the corresponding expression of the transformation is z over z minus a. If the same partial fraction expansion method is used, decompose by the method of seeking coefficients. Then let's take a look at the difference between these two formulas. The same structure for the denominator for the partial inverse Laplace transformation of the module. The above obtained by partial fraction expansion is a constant, and if you use the same method to decompose, then we can get that there is not a form of the first power of z above it. This is the difference between the two. According to such a distinguished form, if we use the same method for partial fraction expansion, we need to pre-process the form of x of z. Then we can divide it by a z in advance. Finally, multiply this z again, just to ensure convergence at z positive infinity. We can make the order of the molecular polynomial of x of z compared with the order of the denominator polynomial. Then k must be greater than or equal to r. Based on this analysis, we can get the basic steps to find the inverse z transform are as follows. The first step, we firstly propose a z for the expression of x of z. Make it into the form like x of z over z. It is a form of true fraction. Then we get target x of z over z. This is true fraction and is partly expanded. The method of partial fraction expansion is as we introduced earlier. Partial expression method for inverse Laplace transform. Then after solving the corresponding expansion coefficient, we multiply both sides of this expansion by z, so that the left side of the equation is x of z. The form obtained later is a form such as z over z minus I. Finally, let's check the inverse z transform table. Thus, the corresponding inverse z transform representation is obtained. This is the general step to find the inverse Z transform. Then in the process of inverse Z transformation, its form has a lot to do with the pole. In other words, the pole determines the form of partial fraction expansion. Then for x of z, its poles are also divided into first-order poles and higher-order poles. First, let's analyze the condition of the first-order pole. For the first-order pole, x of z over z, we expand it into a common form as follows. Then it means that the first term may be the corresponding coefficient of z points. The following items have the same form. They are all in the form of 1 over z minus zm, a constant. Then for the solution of each expansion coefficient in this form, the method used is the same as the method of inverse Laplace transform to solve the coefficient. In other words, that's a formula. So what is the corresponding expansion coefficient am? Am is equal to the z minus the corresponding pole times x of z over z. Then we can make this formula to get z equals to zm. The value at this extreme point is our corresponding pole zm, coefficient of partial fraction expansion at this time. Finally, we multiply both sides of the above formula by z. Then everyone looks at it and sorts it out. The resulting form is as follows. This is the expression. After getting this expression, we can check the inverse Z transform table. Therefore, the form of the inverse Z transform corresponding to each item is obtained. Then everyone can see here, it's all single pole. Mainly depends on the condition of the convergence domain to correspond to what form the original sequence is. In the following, we can make corresponding analysis of related examples. The expression x of z of a sequence Z transformation is known as follows. Convergence domain is the modulus of z. It is greater than 2. We are asked to find the original sequence. We solve it according to the method just now. Let S of z over z. We can get this expression. You can see that its poles are two single poles. So we expand it into the form of partial fractions as follows. We need to use the decomposition method just now. Solve the expansion coefficients of these two single poles separately. So what is A equal to? It equals to z minus the pole 1 at this time. Then multiply this original formula x of z over z. Let z equals to 1. We find the corresponding value of this expression. Then we go through specific calculations. You can see that its specific value is minus 1. Similarly, we can take the second expression. The expansion coefficient is solved and b is equal to 2. So the expansion finally expands to the form of the sum of these two partial fractions. In the end, we put this expansion on both sides, multiply by z to organize. Then everyone can see such a form. At this time, according to the situation of the convergence domain, the modulus of z is greater than 2 is the Carroll sequence. So after we look up the table, the original sequences corresponding to these two partial fractions are in the form of causality. This is corresponding example given by us. But sometimes convergence domain is not only in the form of causality, but also in other forms. Then let's look at the following situations. For the poles 1 and 2 just now, it is possible convergence domain for this partial fraction expansion has the following three situations. The first is the form of chiral sequence, the area outside the circle that is larger than the largest. This is its convergence domain. Then according to the analysis just now, we can see for the basic form of the Z transform, when the modulus of Z is greater than the modulus of A, the corresponding form is the chiral form. Therefore, the original sequences corresponding to these two expressions are as follows. This is the result. This is also the result of the chiral sequence we just mentioned. Then there is another form. For the difference between these two sequences on the right, we can see that its convergent domain may be this ring-shaped area. The modulus of Z is less than 2 and greater than 1. Then, inside these two partial fraction expansions consists of two-part sequences. The part of Z whose modulus is less than 2 corresponds to it. It is an anti-chiral sequence. The part of Z whose modulus is greater than 1 corresponds to this sequence, is a form of chiral sequence. According to the basic form of Z transformation, you can see this corresponding result. The first part is chiral and the second part is anti-chiral. Please notice that there is a minus sign in front of this. This is a form of bilateral sequence, a right sequence and left sequence. Finally, there is a form of anti-chiral sequence, that is, the area within the circle where the convergence domain is the smallest. According to the above, we can see that the modulus of Z is smaller than that of A. The two sequences corresponding to this case are all anti-chiral sequences, which is the form of the sequence on the left. We write the corresponding form of this partial fraction expansion. Then everyone can see such a result. This is very typical unfolding method of partial fraction according to x of z. The general method for finding inverse Z transform. Then what needs to be noted here is the case of different convergence domains. The form of the corresponding original sequence is different. Everyone must pay attention to this. Let's introduce some fractional expansion methods. High-order pole situation. That is, x of z has multiple roots in its expansion. The most important point of this situation. Then, for this situation, we express this basic form of x of z as such a result. When z equals to zi is its m pole. Then we will not discuss other single pole conditions, only discuss the status of this multiple root. For this multiple root expansion coefficient method, with the root partial fraction of the inverse pole transform we mentioned earlier, the method of solving coefficient by expansion is exactly the same. Ask to solve the corresponding partial derivative. This is the situation of the m minus g order derivative. The method of use is exactly the same. Everyone can do a review. Let's look at a simple example. is known that the expression of x of z is the square of 1 over z minus 1. The modulus of z is greater than 1 if its convergence domain find the original sequence. Then you can see it in the topic. Z equals 1 is its double pole. We solve according to the method just now. The first step, x of z over z. So here you can see a single root and two double roots. When we expand the coefficient to solve, we need to solve 3 terms. Then the corresponding denominator part. The first 2 items are determined by the roots. The last item is determined by the single pole. According to the fractional expansion method we just introduced, the corresponding formula for solving the coefficients when rerooting we bring in to solve. No derivation is required for this item. For the first item, the corresponding first derivative is required. Then it is the following 2 formulas. B1 according to this corresponding formula. We take it in to find the first order partial derivative and then calculate minus 1. B2 is directly calculated without calculating the partial derivative 1. Then the corresponding solution method of B3 is the same as the solution method of the single pole just now. It is also 1. So we organize accordingly. X of z partial fraction expansion is such a form. We can determine from the form that the modulus of z is greater than 1. It is all in the form of a Carroll sequence and a sequence on the right. So we check the inverse z transform table, can get such a result. This is the multiple pole case. This is our general method for solving the inverse z transform. All you need to pay attention to is when you regain root, solving expansion coefficient needs to refer to this corresponding formula. Find the partial derivative to solve its decomposition coefficient accordingly. Everyone should pay attention to the specific application of this formula. That's all we introduced today, mainly the partial fraction expansion method to find the inverse z transform, the case of single pole and multiple pole is discussed. I hope you can summarize these 2 issues. Pay attention to the method of solving decomposition coefficients in these 2 different situations. That's all for this lesson. Thanks.